start.
Hello, everyone. Today, we will be updating you on the progress of our project, Navigating the Burn, a study of motion planning algorithms in highly constrained environments. I'm Prathamesh Mehta, and along with me is Anshul Jindal. So, heading to the recap right now. Our goal is to implement different motion planning algorithms against various performance parameters as shown here using barn dataset and Jackal robot. So up till now, we have completed the setup for the barn dataset along with the Jackal robot packages and all the setting up required for it. So we are up and running with the dataset and the robot. While implement algorithms have been run, like we have started with the Dijkstra implementation, and we are done with that from scratch. Right now, rest of the algorithms are yet to be done and implemented, which will be done shortly. As far as the performance parameters are concerned, we have implemented one of the performance parameter, and rest will be implemented shortly. So, as I've said earlier, regarding the implementation of algorithms, the Dijkstra algorithm, both classical and heap-based, have been implemented from scratch, as it is our reference parameter and reference algorithm. Now, regarding the rest of the algorithms to be implemented, we have A star, PRM algorithm, and RRT algorithm, which are yet to be implemented, but will be implemented shortly. The performance metrics which we plan to use, again, like we discussed earlier, is success rate, path length, distance left from the goal, time to solve, and path deviation. So, and we are planning to use the performance metric formula given by the ICRA 2023 competition for the same barn challenge, which can be shown here as the SI formula and the OTI formula. Now, going on to the demo, which will be given by Anshul.
Thanks, Prathamesh. Hi, everyone. I'm Anshul. Let me continue with the presentation and the demo. We'll start with the demo first, which we'll be happy to show you. You'll see different algorithms and their performance in action. And I'll also show the Gazebo simulation and the Jackal robot. Hi there. This is Anshul Jindal, and I'll be demonstrating our project, and I'll tell you about the updates that we have implemented so far. To begin, let's see the heap-based implementation of the Dijkstra's algorithm. This will be used as a standard reference when we move on in the future and compare various other algorithms for our navigation stack. For the Dijkstra algorithm, basically the code accepts a, a graph of nodes and edges. So as you can see here, this is a example where the nodes are numbered from 1 to 5 and the edges are weighted as seen. For the purpose of running our Dijkstra, we have a graph of 200 nodes, which is basically the same thing where node number 81, for example, is connected to node number 115 with a distance of 2608, and the same thing applies to all the other nodes. The Dijkstra code has been implemented from scratch to implement the heap, to maintain the heap property. 2. The the pathfinding the pathfinding algorithm simply returns the shortest distances. We have yet to implement the backtracking to generate the actual path from the source vertex to the target vertex. As of now, as we can see, the output is the shortest distance from the source vertex to all of the nodes. Moving on to the second part, we'll show the barn environment in Gazebo and also launch the RViz view of the Jackal robot. As we can see here, for the gazebo, we have spawned a simple map with fancy boundaries. This map is called Chacal Race, and we have also spawned the Chacal robot at the center of the map. On the harvest tool, we can see that the gazebo robot is accepting external input to move forwards, to move backwards, and also to rotate about the z-axis. As we can see here, these two simulations show us that we have been able to successfully implement the environment and should have no problem in moving ahead with implementing a navigation stack on these environments. For the third part of our demonstration, we'll show how the Jackal robot actually navigates through various barn environments. The the, the setup of the barn environment also comes with predefined elastic band simulator, the elastic band navigation stack, as well as the DWA navigation stack. As we can see on the code here. Then, uh, for the purpose of this simulation, we've set up some random starting and goal positions as tangents along the y direction. The robot should start to move in this world and it should navigate through this path and stop when it reaches the desired y coordinate. So while the robot tries to attempt this humongous task, let's talk a bit about how the code is structured. The performance metric has been taken from the ICRA 2023 competition, the Barn Challenge, where it robustly tells us whether the robot collided, timed out, or succeeded in navigating through the path. The output also shows the navigation time in number of seconds. We have a list of worlds to choose from ranging from 1 to 300. For the purpose of this simulation, we have chosen world number 21, and right now our robot is in the middle of it. All these worlds from 0 to 300 have various difficulties, densities, and layouts. For the future scope, we'll try to generate our own worlds and try to uh, find out the metrics of how well our navigation stack uh, performs against various difficulties, various densities, and etc. As we can see here, our robot has successfully navigated the environment. For now, since we've chosen a pretty big y coordinate, the robot will continue to move forward. However, this short simulation does indicate that the environment has been set up and the robot uh, properly interacts with the environment. That should be it for our demonstration. Thank you very much.
Okay, moving on to the next steps, we plan to integrate the heap-based extra with the main code, and then we plan to perform a comparative analysis on pre-generated and custom worlds. We'll also move on to implement the remaining performance metrics as Prathamesh just mentioned, and finally we'll implement the RRT and PRM algorithms towards the end of the project. And with that said, that's all from us. We'd love to hear our suggestions and feedback. Thank you for your time.
Thank you.